Okay, so we are going to see one final application of max flows and min cuts. In particular, this is an application of really finding the min cut in a directed network. And the problem that we are going to talk about is that of project selection. Okay, so what is the input to this problem? So suppose you are given a bunch of projects. Yeah, so you can think about these as courses in triple IT, which includes classroom courses, or I don't know, maybe paper reading courses, maybe project works that you can do, IPs you can do, and so on and so forth. So you have a set of projects given to you. Yeah, so set of projects P. Okay, and suppose that you have a sense of how much you can derive out of each of the projects. So you have a sense of, in one way of thinking about it is you have a sense of a profit that you can gain by completing this project. Yeah, so for each project pi is to p. Okay, so let me say for each project I, there is a profit pi. Yeah, right, and this is some integer. Okay, so note that I'm not specifying this to be non-negative, positive, negative or anything. So it can indeed take any value. It could be negative, it could be positive, it could give you zero profit. So you might be wondering, what does a negative profit mean? Well, it might just mean that you don't really hope to gain anything out of this project or out of this course, but indeed you think that it's really a waste of your time. So in your mind, it's like a loss that you are incurring by doing this course. Okay, on the other hand, there might be some courses or some projects which will really add value to you, and those are the projects which you categorize to be giving you some positive profit. Yeah, so in general the profits pi can be either negative or positive. Yeah, we are not considering zero profit cases. Yeah, but because essentially you will just not do them. Okay, in some sense. Okay, now what is the objective? Well, the objective is to pick a subset of projects that gives you maximum profit. Okay, right? So among all the projects that are available to you, you have to pick a subset of them such that the total profit is as much as possible. Now, I'm sure many of you have started to wonder that what's so non-trivial about this problem? I can just pick the ones which give me, well, which give me positive profit. That's all. That should be a solution, right? Clearly, that's the maximum that one can derive given a bunch of projects. Okay. So clearly, we need to add some constraints to this problem in order to make it non-trivial. Okay. So the constraints that we will add to our problem are what are known as precedence relationships. Yeah. Okay. And this is best described in the form of a graph. So suppose that I will draw a directed graph where each node will specify one project in your set P. Okay. So let me actually show this by picture. So suppose these are your projects. draw it a bit differently. Yeah, suppose these are your projects. Okay, and let me introduce some edges in my graph now. So suppose these are the edges. Something like this. Okay. Great. Okay, so what does this graph mean, right? So it means the following. So suppose this is the project I, this is the project J1, and this is the project J2. Okay. So what this graph is saying is the following. The semantics of this graph is the following, that if I look at any project I, right, then if I want to finish project I, then I must finish project J1 and project J2. In other words, if I look at a vertex in my graph and I look at all the outgoing edges from this vertex, then whichever projects are at the head of these edges must be completed in order to complete I. Okay, so some of you might be thinking that this is an unnatural way to denote this precedence relationship. The arrows should have been in the reverse direction. That's a more natural way, that you first finish the project J2 and then you can only finish I. But there is a precise reason that I have shown the edges like this. So these are opposite to what would be a more natural choice of the direction. But as you will see that this helps us design the algorithm which we'll be using to solve this problem. Okay, so this is my so this graph essentially now puts some constraint to the set of projects that I can choose. All right, so I just cannot choose any set of projects that I want. Whenever I choose some projects to be completed, I have to make sure that whichever projects has like a precedence relationship to this project should also be included in my set. Yeah, so in particular, let's see. So suppose you want to pick I. Okay, you really think that I is going to give you a very good profit, but then because of this precedence relationship, you must finish J1, you must finish J2. But remember, if you want to finish J2, you must finish this guy as well. Similarly, if you want to finish J1, then you have to actually finish this guy as well, right? And this guy as well. So this is, this example is not really the best one. It turns out to be that you essentially have to, finish everything if you want to finish I. But okay, on the other hand, suppose you only wanted to finish J2. You don't care about I or any other ones. Suppose you only wanted to finish J2, right? So suppose you only wanted to finish this guy, this project, then the only project that you need to finish before that is this one. Okay, so let's say J3. Yeah, so you might just choose to complete J2 and J3 and then nothing else. So that's up to you. But whenever you include the tail of some edge, then you have to make sure that you have also included the head of this edge in your set. Okay, so now I hope you are pretty much convinced that this problem is non-trivial. Yeah, you cannot just pick all the projects which have positive value, because that might be an infeasible solution. You might have to include some of the projects which have negative values, just because there is some precedence relationship among the projects. Okay, so I hope the definition of the problem is clear to you. So in the next video, we would be talking about how to reduce this problem to finding the minimum cut in a certain graph. Okay. Okay. So in the last video, we defined this project selection problem, and now we are going to see how to reduce this problem to finding the minimum cut in a certain graph. Okay. Now there are straight away some issues in reducing this problem to minimum cut. So let me list them out. Yeah. So issues in reducing to min cut. Yeah. And these are the issues that often arise when you hope to solve a problem by using either max flow or min cut, where it's not readily clear how the network looks like. Yeah. So the first issue, of course, is source and sink. Source and sink. Okay. The second issue is how about the capacities? So I have to worry about what capacities to add to each of these edges, and remember they have to be positive. Yeah, they have to be positive, and the reason I am stressing upon this fact that they have to be positive is because there are some negative quantities in my input. So there are some negative profits for some projects, and we have to do something about them, right? We have to use only positive capacities, otherwise I cannot apply max flow or min cut algorithms. So we have to see how to handle the negative in numbers in my input. And in fact, if you think about it, the third issue is the objective function. Why is this an issue? Well, remember, I am trying to maximize my profit. On the other hand, I'm telling you that I'm going to use the min cut theorem, which is a minimization objective. Clearly, both of them are optimization problems, but one is maximization that you are going to solve, that you want to solve, but the one that you are trying to use is a minimization problem. So how do we, transform a maximization problem to a minimization objective? So these are the, at a high level, these are the three issues that we are going to talk about. Okay, so let me give you the construction first, and then we will see why this construction works. Okay, so the construction is going to be as follows. Suppose the blue edges, the blue vertices are those which have positive profits, yeah, and the red projects are those which have negative profits. Okay, so I have separated out the positive profit projects and the negative profit projects. Now I'm going to add a source to my graph. Yeah, and I'm going to add an edge to all the blue vertices in my graph. So these would be some new edges that I'm introducing. Similarly, I'm going to add a sink, which is T, and I'm going to add an edge from every negative project to this sink. Okay, good. So this issue is apparently solved. Of course, I have not convinced you how this helps, but at least now I have a source and a sink in my construction. Okay, how about the capacities? Well, if I look at a blue edge, I will set its capacity to be the profit of this project I. Yeah. So if I look at the edge SI, for example, the capacity of this edge is going to be precisely PI. Similarly, the capacity of this is going to be PJ2. Okay. When I'm looking at a red edge, remember here I cannot do this because the profit of the red vertices are negative. Yeah. So how do we convert a negative quantity to a positive quantity? Well, simply by putting a minus sign. Okay. So the capacity of this guy is going to be minus of Pj3. Okay. And similarly for the other edges. So this defines the capacity for the blue and the red edges in my graph. But note that I also have to worry about the black edges in my graph. What are the black edges? Well, the black edges are the edges that are derived from the precedence relationship. So this is part of the input. Yeah. These are not edges which I have drawn out, drawn for my construction. These are the edges that are already given to me. But I now need to add some capacities to these edges in order to finish the construction of the flow network that I am going to build. Okay. Now, in order to do that, I have to tell you a bit about what are the semantics what are my intended semantics of this construction? Okay, so the intended semantics is the following. So this is what I want. So this is intuition, right? Okay, so what I'm addressing now is capacities of black edges. Okay, so the intended semantic is the following. So let's say, remember, I want to apply the mean cut algorithm to solve this problem. So the mean ST cut. So suppose I have a mean ST cut, yeah, and the mean ST cut looks like this. So I don't know, maybe the mean ST cut looks like this. Okay, let's call this A. Now, intuitively, we want projects included in A to be selected. Okay, so this is the intended semantics of my construction. So the idea is I will construct this flow network, and then I will find the mean ST cut. Let's say A is one side of the cut, which is the S side of the cut, and the idea is that I should be then able to select all the projects that are included in the A side. Yeah, it's not clear why this will solve the problem, or minimizing such a cut should give me the maximum profit and all. Those will come later, but this is at least what I intend to do. Okay, now if I intend that, then what should I set the capacities of the black edges to be? Well, remember, the set of projects that I select is feasible only if whenever the tail of an edge is included in A, then the head of an edge should also be included in A. Okay, so if that is what I want, then clearly this red cut does not give me a feasible solution to the problem that I'm trying to solve. Remember, this is a feasible cut, that's for sure. There is a feasible cut in my graph. This is an ST cut, but it does not solve my problem. Why? Because if you select the projects that are included in A, in particular these three, then clearly this is an infeasible solution, because if you need to finish I, you have to finish J2. Yeah. So in the language of this picture that I have drawn, here is what I want. I want that when I compute the mean cut of my graph, then a black edge should not be part of that cut. Okay? Because if a black edge is part of that cut, that means that the A side of the cut is an infeasible solution to my project selection problem. So I either have to so essentially the black edges should entirely be contained either on the right hand side of the cut or on the left hand side of the cut. There should not be any black edge that should cross my cut. Now, how do I make sure? Now you might be wondering that, okay, how do you make sure all this? I mean, how do you make sure that the ST cut which you have found does not have any black edge crossing that cut? Is it even reasonable to believe that this is possible? Now, the first thing I want to claim is this is actually reasonable to believe. And the reason is the following. So if you think about for 30 seconds, then you will realize that the mean cut of this graph is already finite. Even if I have not assigned any capacity to the black edges, if I just look at the capacity that I have already sort of assigned to the blue and the red edges, there is a cut which is of finite capacity. Right? In fact, there are two cuts that are of finite capacity. One where all the blue edges crosses the cut, and the other one where all the red edges crosses the cut. Yeah. So these have finite capacity. Okay. And remember, those are feasible solution to my project selection problem as well. Why are they the feasible solution? Well, if you look at the cut, so what I'm saying is, if you consider this cut, right? Then what does this translate to in terms of the project selection problem? It just translates to the fact that you are not picking any project at all. The A side of the cut is empty as far as projects are concerned. So you are not picking any project, but that's a feasible solution. You are free not to choose any project. On the other hand, if you choose, so suppose you choose this entire thing, yeah, that's also a feasible solution, yeah, and that has a finite capacity. The capacity is only the capacities of the red edges in my graph. And what does this solution correspond to for the project selection problem? That you have selected all the projects in your input. Yeah, you have decided to finish all the projects. This might not be the best that you can do, but these two are clearly possible solutions to your problem. So I know that there is a possibility of finding finite mean cuts in my graph, which will translate to feasible solutions to my problem. Okay. So given that, now I want to rule out the following fact, that when I compute the mean cut in my graph, it should not have any black edges crossing this cut. Okay. If I want to rule that out, now what should I do? Well, if you think about it again, I should simply do the following. I should assign a capacity of plus infinity to all the black edges. Okay. So all these edges, all these black edges will have, again, what is plus infinity? It's a very large value. Yeah. So suppose it's much bigger than the summation of all the positive PIs or something like that. You can choose any large value you want, which is large enough. It's so large that the mean cut the mean ST cut in this graph will never include a black edge. Yeah, and this is clearly true because, as I said previously, that all the blue edges or all the red edges, they already form a mean cut. So if you assign the capacity of the black edges to be much larger than if you effectively infinity, then there is no reason for your minimum ST cut to include any black edge. Okay. So that's the reason intuitively that why I am placing the capacity of infinity on the black edges. Okay. So let me just write this down. So this is capacities of black edges. So assign a capacity of plus infinity to all the black edges. Okay. And that finishes my construction. Okay. So I claim that if I construct this network and if I find the minimum ST cut using whatever your favorite algorithm, then all the projects, all the vertices that are not source, that are included on the A side, will give you the set of projects that maximizes your profit. Yeah. So the theorem is, if AB is a min cut in the above graph, then the set A minus, of course, S, because S is a fictitious, it's a dummy vertex, right? It's not part of any project. Then the set A minus S is the set of projects with maximum possible profit. Okay, and this is what we are going to sort of prove in the next video. Okay, so in the previous two videos, remember we had introduced the project selection problem, and we showed a reduction of that problem to finding the minimum cut in a certain network. Yeah, and the way we had constructed this flow network is the following. We added a source and a sink, Then we added a blue edge from the source to every positive vertex in this graph. We added an edge from every negative vertex to T, and the capacity of the blue edges is the profit of a blue vertex, and the capacity of the red edge is the capacity of the corresponding red vertex, and the capacity of the black edges, which are the edges that define my precedence relationship, those have a value of plus infinity. Yeah, and remember, the intuition behind doing this is that when I compute a min cut in my graph, these black edges should not cross the cut. Yeah, and the reason I want this is because that will directly translate to a feasible solution to my project selection problem. Okay, so then I ended sort of the video with this theorem that if AB is a min cut in this constructed graph, then the set on the A side without the source S is the set indeed that gives me the maximum profit. Yeah. So why should this be the case? So let's see why we think that this should be correct. So let me copy this diagram. Okay. Okay, great. So suppose I give you some min cut. Okay, so fix some min cut. Some min ST cut in G. So this network is called G, and I have fixed some min cut in G. Yeah. So the first claim that I want to make is that a black edge cannot cross this cut. Yeah. So the claim is black edge cannot cross. Cannot cross this cut. Yes, and this should be immediately clear, because if a black edge crosses this cut, then the value of this cut is infinity. But as we discussed in the last video, that there is already a cut. There are in fact two cuts in my graph which have finite capacity. So why should the min cut algorithm select a cut which has infinite capacity? It can very well just select the trivial cut, which is S on one side and everything else on the other side. That's clearly a finite capacity cut. So any min cut in this graph cannot have an infinite capacity, which translates to the fact that no black edge can cross this cut. Okay, so that's one thing. So let me try to show actually how such a cut can look like. Yeah, okay. So one possibility of min cut is the following. Right? Yeah, this is a possible min cut, right? So if you notice, there are no edges. So this is A. Remember, this is the A side of the cut. This is not A, right? This is the A side of the cut, and whatever is not inside this red lasso is in B. So if you notice, there are no black edges crossing this cut. And indeed, if you think of, so if I give you this min cut, then what is the solution to the project selection problem? Well, it's the projects J2 and J3. Yeah, and this is a feasible set, because okay, we will first finish J3, then you will finish J2, and that's perfectly fine. So any minimum cut in this network will always have no black edges crossing this cut. Okay, so now what is the capacity of such a cut then? So capacity of any such cut. So this should then just be equal to the capacity of blue edges plus the capacity of green edges. Red edges. I'm so sorry. Red edges. Okay, good. And that's clearly, it's obvious if you look at this red cut that I have shown here. All right, so good. So if A is this side of my cut, then what is the capacity of the blue edges? So which are the blue edges that are crossing from A to B? Well, these are those blue edges that go from source to the blue vertices that are on the other side. And what are the blue vertices? Well, the blue vertices are those which have positive profit in the project selection instance, right? So I can just write this as equal to summation of I does not belong to A such that Pi is greater than 0, and I'm summing up over all the Pi's. Yeah. So if you look at this picture, these are the two edges that I'm talking about. So they belong to the other side of the cut. They does not belong to A, and they have positive capacities. So this is the total capacity of the blue edges. However, the red edges, it's just the converse, right? So these would precisely be the edges from the red vertices that are inside A to the sink T. Yeah, and what is the capacity? Well, the capacity is minus of the profit. Okay, so this would be, so let me just write this as plus minus of summation Pi, where I now belongs to A and Pi is less than 0. Okay, now let me write the first term as something slightly different. So I'm writing this as C minus summation of Pi, where I belongs to A such that Pi 0 minus summation Pi, I belongs to A such that Pi is less than 0. Okay, where what is C? Well, C is the total positive profit in the given instance. So this is overall I, all I such that Pi is greater than 0. So this quantity C, it's if you just add up all the positive profits, yeah, I'm not considering the negative profits here. If you just add up all the positive profits, then that defines your number C. So this is a fixed quantity, yeah. So I am just writing, this is only the positive profit projects on the other side, on the A prime side of the, on the B side of the main cut. So I'm just writing that as C minus those which are on the A side. Yeah. So this is just another way of writing it. Now, this now becomes C minus, okay, what can I now say about this quantity? So this is minus of the summation of these two. But if you think about it, this is precisely the profit that you will derive if you select all the projects that are on the A side. Yeah, this is precisely the definition of your profit. So this is minus the profit of A minus S. Yeah, so you are adding all the positive profits and all the negative profits which are on the A side. Yeah, so this quantity is C, which is the total positive profit in your instance minus the profit. Okay. So seems like we're almost there. Why do I say that? Because remember, I want to find a cut, or I want to find the set A which maximizes this quantity. Yeah. Now, if I want to maximize a certain quantity, then that's equivalent to minimizing the negative of that quantity. You see where I'm going, right? Because remember, I started with a maximization objective, but I have to I've reduced the problem to a minimization objective, which is why this minus sign before this quantity is great for us. Because if you think about it, what we really want is to minimize this quantity which is inside the negative sign. Yeah. But now you might say that, well, you have another quantity C, which is a positive quantity. In fact, this quantity is essential because that's what makes this entire thing positive. Yeah. Otherwise, if this thing was negative, then our mean cut problem was ill-defined, because I cannot find I cannot solve the mean cut problem where the value of the minimum cut is negative. So this is really required. But now what you have to understand is, if I minimize this quantity, then why should this maximize this quantity? Well, the only thing that remains to be argued is that this quantity is independent of the cut that you are finding. Yeah. So essentially this is a constant as far as the cuts are concerned. It doesn't matter which cut you are finding in your graph, which cut you are finding in this graph. This quantity is a fixed constant because it's a part of the input. It's just the summation of all the positive profits in your graph. Okay. So now what we have arrived at is that the capacity of any minimum cut, yeah, is some constant quantity minus the total profit that I can derive by taking the A side of the cut, right? So this implies that maximizing profit A is equivalent to minimizing C minus profit of A minus S. Okay, and your mean cut solution is doing precisely that, right? Just from the fact that the capacity of the cut is exactly this quantity. So this is how you solve the project selection problem, by reducing it to mean cut. Okay, so you should think about the running time of this algorithm, right? What does it depend on, and so on and so forth.